All right, so we did these notes in class. I'm just going to go over them for anyone who was absent. And it's just on dilating points in the coordinate plane and the difference between a stretch and dilation. And a stretch and dilation part is pretty easy. Dilating a point when the center is at the origin is pretty straightforward. The only part that requires probably some explanation that you want to listen carefully on is dilating a point where the center is not at the origin. But we'll start here. We'll say what's a stretch and a dilation. How are they different? Well, they're different in the sense that a dilation scales up all dimensions, or both dimensions, by the same factor, where a stretch might have a different scale factor for each dimension. So you might have a rule that looks something like this, where you take some ordered pair, and maybe you scale the x up by a factor of 2, and you scale the y dimension up by a factor of 5, so the dimensions are stretched differently, so they're no longer proportional, the original in the image. Whereas a dilation, you take this pre-image point, and you scale it up, and this is just an example, but maybe you scale up the x by a factor of 3 and the y by a factor of 3, so the new point and the original point, or the new figure and the original figure, are proportionate. They've been scaled up by the same factor. So identifying the stretch and dilation is pretty straightforward. You can look at the rule and see that the scale factor is different for the x and y, so we know that's a stretch. Here, just visually, we can see that these two shapes are proportionate. And if you wanted to verify even more, you could, let's say, draw a line between all the corresponding points, and you'll find that they all intersect at the same center. But this is an example of a dilation. And in this last example, we've stretched this figure, or we've shrunk it down vertically, but we've kept it the same horizontally, so the dimensions are not the same. So we know that this is a stretch. All right, so you can look at those and real quickly identify which one's a stretch and a dilation. And then we'll go on to the next page. All right, when we dilate a point, when the center of dilation is at the origin, all you have to do is scale up each coordinate. So if we're going to dilate our point by a factor of 2 with a center at the origin, all you have to do is double the x and double the y. So the original x is at 1 and the original y is at 3. We're just going to double it, so it's going to be 2, 6. And that's C prime. Okay, on this one you're going to half each coordinate when the center of dilation is at 0, or is at the origin. And again, it just means you half the x and the y, and you half the x and the y. In this case, you're going to connect the dot. So that means our rule for a dilation, when the center is at the origin, is to simply multiply both the x and the y by the scale factor of k. So that's the rule. So down here, I'll do these 3. You can do the bottom 3. If we dilate the point -3, 5 by a factor of 2 with the center at 0, we're just going to double both the x and the y. Here we're going to make each x and y part 5 times bigger, so we get 2 times 5 is 10, 8 times 5 is 40. And then we're going to make this point a third the distance back to the origin, or to the origin. Actually, I think I said that wrong. It's going to be, the new point is going to be a third of the distance as this point is from the origin. Either way, we're going to take 6 divided by 3, 24 divided by 3. All right, so you do these 3 problems. My only suggestion here is anytime you multiply, or just in general, whenever you're dealing with fractions or decimals, leave your answers in fraction form. It's always probably kind of the preferred form. Okay, so do those 3. And then we'll move on to this last part, which takes a little bit more explanation. This time we're going to dilate a point with a center that's not at the origin. So that's what this says. It says dilate a point by a factor of 1/4 whose center is at t. Okay, so that means we're going to bring G in closer. And the new distance to G is going to be 1/4 of the original distance. And so the distance here is diagonal, which means it has two components. It kind of has a vertical part from T up to G, and it has a horizontal part from T over to G. Well, that vertical and horizontal part are the slope, or the rise over the run. So the first thing you want to do is identify rise and run from the center to the point. Okay, and that's important. So from the center to the point, we rise, well, we're going from 1 to 9, so we rise 8. And we run, well, we're going from 8 over to -4, so 8 and 4 makes 12, but we're going, as we went up 8, we go left 12. And we're going to leave our slope in this form because this is acting like a vector that has magnitude and direction, and we don't want to reduce it because otherwise we'd be saying G is maybe this far away to start, and we're bringing it 1/4 of the distance. But we want to say that G is this complete distance of up 8 over 12 and 1/4 that distance back to T. Okay, so now the idea is, well, okay, I'll show you the simple way to do it when you have a graph, and then I can show you the formula that you'll use later on. The original distance from T up to G was 8, and we just want to go 1/4 that distance. Okay, so 1/4 of 8. 1/4 of 8 is 2, and so we just have to go up 2 from a value of 1. Right? We're at 1, we just have to go up 2. All right, now let's do the x part. It was originally -12, and we just want to go over 1/4 of that from 8. Well, 1/4 of 12. 12 divided by 4 is 3. So all we have to do is go over 3. So up 2 over 3, there's our point. This point now is a distance that's 1/4 the original distance. Okay. Let me show you kind of a way to write that out symbolically. What we did was, first we found our y value. And the original y value was 1, and we added a distance to it. Remember, we just went up 2. Well, we added a distance that was 1/4 of the total distance, which was 8. Okay, so 1 plus 1/4 that distance. Remember, 1/4 of 8 was 2, and 1 plus 2 is 3. So, yes, we went up 2 from 1, but notice from the x-axis we went up 3. Okay, so now we'll find our x. The x started at 8. And we went backwards actually, a distance of 3. So we'll see that here. We're going to add 1/4 of the original distance, which was -12. Okay, so now we have 8 plus 1/4 of -12 is -3. 8 minus 3 is 5. So our x coordinate of G prime is 5, and our y coordinate of G prime is 3. Okay, so you're going to do this one. And yes, this one's pretty easy to do with the graph, but you need to be able to do this formula so you can do it without the graph. At the top, we'll write the rule. Now, the rule says, if you're going to dilate this point by a factor of k with a center at AB, your new x, well, we're going to get to our new x by starting at A and adding our scale factor times the distance between those 2 points. So x minus A. And our y value, whoops, I didn't mean to put parentheses there. That shouldn't be there. All right, our y value is going to be b, that's our starting value, plus our scale factor times the distance between the y's. So y minus b. All right. If you have questions, and you probably will, we did a few more examples in class that were not in the notes. But if you have questions, just come see me. Do this problem, and like I said, maybe do it the easier way, because on the graph it's easier as visual. But after you've done it visually on the graph, do the formula as well over here on the side. All right, that's it.